Let me re-explain one of these, the volume part of this reaction here. So, in this case, where I'm decreasing the volume, what you need to realize is that there's two gases here. They have a total of 13 moles, 10 and 3. And then there's one gas here, the N2, and there's 2 moles of it. Moles for gases, if you remember from chapter 6, represents volume. Because for an ideal gas, there's 22.7 liters per mole. So more moles, more volume, less moles, less volume. So when there is a decrease in volume, the reaction will go to its smaller side to fit. So a decrease in volume will cause a shift to the right to the smaller side. And if N2 is on that side, a shift towards this means shift right means we're generating more products. There's more products, then this will increase. Okay. Or you can think about it. Okay, you can think. Okay. I'll save this out if you want to ask me more later. Okay. Anybody else have a specific question? Oh, cool. Oh, yes. Okay, Gary.
You need 3 on spring 2011.
Okay, spring, exam 2, spring 11, number 3. Spring 11, page 78, number 3. What's the conjugate base? Is that the one? The conjugate base of that iron species? Oh, wait, what? Here we go. Okay, what's the conjugate base of that thing right there? So that's implying it's an acid, which it definitely would be. Anything with water, that would be neutral, and then a transition metal would make it an acid. So it's donating a proton. So one of the 6 waters will lose a proton. So see how there's 6 waters there? One of those 6 will lose a proton. So obviously not that. That's almost identical. That's ridiculous. This gained a proton. That's crazy. It's D. Here, there's 5 waters left, and one of those waters became an OH because it just lost a proton. Is that okay? Okay, cool. Who's next? Yes?
Can you do number 11, same test?
Number 11?
Spring 2011.
Spring 2011.
Yeah.
Oh, same dealio here. This one here?
Yeah.
Okay. Which of the following would be best to buffer an aqueous solution of pH of 4.5? Okay, we'll take a look at it first. Let's see if they're all buffers. They're all weak, because none of them are on the strong list. And one has a proton and the other one doesn't. So they all could be buffers. However, we want a buffer that's close to 4.5. How would you do that? Well, the buffer, how that would be estimated is by the pKa. So if you take the negative log of each of those Kas and see which one gets a Ka closest to 4.5, and that would be your answer.
Okay.
Yeah. Cool. Who's next? Yes?
Can you do number 7 for spring 2013?
Spring 2013. Let's flip over there. Number 7. Is it this one?
Yeah.
Okay, spring 2013, page 71, number 7. Okay, 1 liter, 0.5 moles of that reacts with this. What's the resultant pH? Okay, so let me write this down. I think that'll be a little easier. We've got HCl. It's 1 liter, and this is 0.5 moles, a molar, plus strontium hydroxide. This is 1 liter, or 1 liter of, oh, I wonder if it's cut off. Oh, I see what happened. Yeah, thank you. I didn't see that number, 0.25 molar. Okay, let's write out the reaction, see what happens. These are strongs, so it's going to go 100% to the right. So this will be strontium. This is a neutralization, strontium chloride and H2O. It looks like I need 2 of these, 2, is that all balanced now? Okay, I think it is. And so, if I multiply these, I'll find out 1 times 0.5, that'll give me the moles. 1 times 0.5, that's just 0.5 moles of this. And then I have 1 times 0.25, that's 0.25 moles of this. Okay. So, yeah. What I want to do, I want to see, because of the question, let's go back to the question for a second. If there's extra acid, I know my answer is A or B. If they're equal, then I know my answer is C. If it's greater, I know it's D, and then E is just ridiculous. Okay, pH usually goes around 14. Okay, this was just for fun because I thought it looked funny. Okay, so let's check this out. Let me get a different color pen, and I'm going to say, well, 0.5 moles of HCl. I want to see how that compares to my strontium. So I'm going to say, well, there's 1 mole of the strontium hydroxide for every 2 moles of the HCl. Oh, so that gives 0.25 moles of the strontium. Hold up. That's exactly how much I have. So they're in molar equal stoichiometric ratios. That means this pH is 7, that's right, because it's neutralized. Yeah, because I have the right amount of each. Is that okay?
Yeah. Thank you.
No problem. Good. This would be a relatively, I would say this is not an unusual question. Okay? All right, yes?
Winter 2007, number 18.
Winter 07, flipping over there, Winter 07, number 18, this is page 94. This one right here, right? Okay. I want the pOH of an aqueous solution with these 2 concentrations. Okay, I have to write this one down too. So let me write this down. Again, that's page 94, number 17, Winter 07. Okay, KOH concentration equals 0.5 molar. And then there's the cesium hydroxide concentration equals 0.75 molar. Okay, these are both strongs. Okay, that means this is going to equal its hydroxide concentration. Is that okay? However, this one involves a little more thought because there's 2 of them. It's generating 2. So, if I have 0.75 molar of the cesium hydroxide, and then there's 2 moles of hydroxide for every 1 mole of cesium hydroxide. Did I write that correctly? Yeah. Oh, that's weird. That's a misprint. This really should be barium, but that's okay. The math will still work out, but really that's a misprint. It should be barium. Anyways, that probably means nothing to anybody. That's okay. 1.5 molar. It doesn't change your numbers. This is now 1.5 molar. So you see, because I'm generating 2 hydroxides for each molecule. So now, in the first case, let's write this down, hydroxide. I have 0.5, and I'm going to add another 1.5. So if I go OH minus total is going to be 1.5 plus the 0.5, that's 2. Now I can find the pOH is the negative log of that number. Is that okay? Okay. And I don't know, it'll be A or B. It's a pretty small number. Cool. Who's next? I should mark that down. That should be barium. Okay, who's next? Oh, we ran out of people. Oh, yes, okay.
We need 19 on spring 2009.
Spring 09, number 19, is that this one?
2010, yeah.
Oh, spring 10. Hold up.
Page 86.
page 86, even better. I can count faster. Number 19, spring 10. That's this one. This crazy. Okay. I don't even remember this one. Let me see. Phosphate, I'll leave it here so you can see it too. Phosphate buffers are commonly used in biological systems. Okay, first sentence irrelevant. Scientist mixes together so much of each. The resultant solution is this adjusted to the desired pH with 6 molar sodium hydroxide. So we want the initial before the addition of the sodium hydroxide, and then probably here after. Do you want A and B?
I don't care. I had a question,
Okay.
like, why didn't you use K to for pKa?
Oh, I don't know. Let me see. So right here,
Yeah.
let's see. I think I did use Ka2.
Yeah, why?
Oh, why I used Ka2. Okay, cool. This is a much easier question to answer now. Let's write the acid-base pair. Whenever you have this, here's what I would do. Write the buffer pair out first like this. You'll notice I removed the sodiums because the sodiums are just spectator ions. So I'm just writing it without the spectator ion first. Now what I'm going to do is I want to write this as a reaction. And I want to write it because it's from a polyprotic acid, I'd like it to be in the acid direction. Meaning, here's my acid and here's my conjugate base. Is that okay? So I'd like to write the general equation for an acid, especially because it's confusing when they come from a polyprotic. And writing that out will help clarify things for you. So what I'm going to do is write H2PO4 minus plus water. My typical reaction, it donates an acid, or it donates a proton, become this. Okay? Now is where you start thinking of Ks. This is now the second loss of the proton. So it's called a Ka2, and that's why I use that. Okay? So again, one more time. If you get a question, this is for anybody, in this case where you have these compounds like these that come from a polyprotic, in our case phosphoric acid, first what I would do is write them down without the sodiums or whatever the spectator ion is, write it down without that. And then, once you have that, write down the reaction that these two would undergo with the acid part in the reactant. And the base part, that's this one, in the products. Write that out, and then it's easier to determine what K you use. We used Ka2 here because this is the second loss of a proton. Originally, the first loss would look like this. H3PO4 phosphoric acid plus water goes to H2PO4 minus plus H3O plus. The first reaction I have written down right now is Ka1. So that's why I wanted a Ka2. Okay, cool. Good question. Who's next? Yes?
Well, with that one, would you know that it has would you know to use K2 because they give you K3, and since they give you H2, you have to use like the K. I don't really make sense.
Not yet. But if you made sense, I would totally answer that question. Because there's different Ks, you're right. Well, I give you all three to maximize the amount of confusion.
Yeah, I guess how do you know that there would be an H3PO4? Would you just know that because you gave a K3?
Oh, okay. How did I know that? What I would want to do, how did I know that this was birthed from H3PO4?
Yeah.
Well, when I write these down, I'm starting to think, okay, what's the neutral form of this? Let's add protons till it gets neutral. So if I add one proton to this, I would get this. Or if I add two to this, I would still get the same thing. That's what you want to think about, especially when they're both negative and it kind of tweaks you out a little bit. That's exactly what I would do. Is that okay? Okay, good. Who's next? Yes, okay. Okay, yes, more clarification. Yeah.
You use Ka2 because the two given molecules, when you take away the sodium, you get the acid and then the conjugate base.
Uh-huh.
And then you
Uh-huh.
And then figured that like you're taking away a hydrogen, therefore it's Ka2.
That's exactly right. You said a lot, that's hard to repeat, but yes. If, just to give you an alternate example, if it was this pair, then the K you'd be using is K3, because that's for the third loss of the proton. Yeah. Okay. Cool. Yes?
Can you do B of that problem?
B. Oh my gosh, this problem's killing you all here. Okay. Let's see. Determine the amount of base required to adjust the pH. Okay, so what I'm going to have to do is use a little buffer problem here. What I did, no wonder if it's a little confusing, I did multiple steps in one on this third line here. So that's why it might look crazy. Okay. Just do this. Yeah, let's use this page. Okay. All right, I have my buffer stuff right here. There's my buffer. And then I'm adding sodium hydroxide. This is 6 molar. And I want to make the pH equal to 7.4. And I want to know what volume to add to make that happen. Okay, so I've got, first I know it's a buffer, so I know I've got pKa plus the log of the base of the acid. I know I've got that action, okay? I know what this is. This is 7.4. I know what that is. This is, let's see if I even figured it out. Oh, I didn't. It's the negative log of the Ka, which is Ka2 specifically, or 6.3 times 10 to the minus 8. Okay? So that's that. What I don't know is this. Can anybody find this number for me really quickly? That'd be helpful. What the log of B over A is going to do?
7.2.
Okay, this is 7.2. The log of B over A is going to raise this 0.2. So that's what I want to do. I want to figure out what B over A is going to be to raise this value up to 0.2. So that 7.2 plus 0.2 will equal 7.4. That's what I'm trying to do. Okay, but I just don't know those numbers yet. So that's the problem. Okay, so let's see what I have. I have some information from the previous part of the problem. Let's see. I know that HPO4 2 minus, that's 1.8 molar, and it's 400 milliliters. And the other one is H2PO4 minus. This is 130 grams. Yeah. Okay. So to do the log of the base over the acid, I need this in molar, okay, or concentration units. So for the HPO4 2 minus, one more thing. Before I get to that part. Because I'm adding something to a buffer, I'm going to use the stoichiometric table. So I'm adding, in this case, a base, the sodium hydroxide.
Is that where you got the plus X and the minus X?
That's exactly why, yeah. Which you'll see in just a moment. So I'm adding sodium hydroxide to my buffer. Because it's a base, I'm going to add it to the acid part of the buffer. Is that okay? So the acid part of the buffer, I'll ask everybody, is it the top or the bottom? Which one's the acid? The bottom, it's the one with more protons. Okay? H2PO4 minus plus my hydroxide is going to form HPO4 2 minus plus H2O. So it took a proton from the acid. This goes 100% forward because the hydroxide is my strong base. It's from sodium hydroxide. Okay? Now, let's see how much I have. My first question is how many mole, well, let's do the easier one. Do I have moles of that? No, I don't. How many moles of this do I have initially? Well, let's do a different color. For the H2PO4, I have 130 grams of this, okay? I would need to multiply this by the molar mass to change this to moles. And it's 119.98 or 976 grams. So that's the amount of moles of that. Is that okay? Let's skip this one for a second. How many moles of this do I have? Well, let's see. I have 1.8 molar, and I know the volume, it's 0.400 liters. So that's the moles of that one. Is that one okay? Okay. Now I want to know, well, how many moles of this do I have? Hard to say. We can, let's just, I used in the question X. You could use any variable you want. Okay. In any buffer problem, that's always going to be the least amount. I'm adding just a tiny bit of X, in this case, to shift the equilibrium over. So what I'm going to do is subtract that off of here, because it reacts all the way, and add it to here. Now, I've got 0. This is 1.8 times 0.4 plus X, and this is 130 divided by 119.976 minus X. So this is A, and this is B. That goes into the Henderson-Hasselbalch equation from up above. Is that okay? The problem is, you gotta solve for X. So you wouldn't need the quadratic, but you would need a little algebra once you move things over to the other side. Is it okay? Okay. Cool. Who's next? We'll take like 1 or 2 more, if there are any. Yes, you've been waiting for a while. 2000, did you say 13? Okay, 2013. Let me flip over there first. Number 9, you said? So that's this one here. Does that look familiar? Yeah. Okay, this is page 71, 2013, number 9. How many oh, buffer? Y'all love buffers. Okay, I need another page for this as well. We have acetic acid, 0.200 molar acetic acid, and I don't know the volume, so many milliliters, and that's mixed with sodium acetate. Okay, and that is 13.2 milliliters and 0.200 molar. Oh, same. Okay, and I want a buffer of pH equal to 4.2. Well, again, because it's a buffer, I'm going to write out my equation. This is equal to pKa plus the log of the base over the acid. pKa is 4.74 in the table on the back of the exam for acetic acid. Okay, so this is a given. You'll look on the back page for that number. Plus the log of the base over the acid. Remember, this will equal 4.2. This is kind of like the other problem, where I want the number to be 4.2. I know pKa, and I need to figure out what the right-hand side is going to be to make this all add up correctly. So the base is the bottom one here, which is let me see how many milliliters are mixed with. Ooh. Okay, let me solve this down below. Because these are mixed together, and let me call this volume V. Okay, because these are mixed together, let me solve this down below. Okay, for the acetic acid, NaC2H, or sodium acetate, I want to find the moles of this. So the moles would be 0.200 molar times 13.2. This will give me millimoles. That'll give me millimoles of the acetic acid. I can also, for the HC2H3O2, the acetic acid, that's 0.2. And I don't know its volume, but this will give me the millimoles of acetic acid. Okay, to get the concentrations now for the sodium acetate, what I would do is say, well, millimoles of NaC2H3O2 divided by the total volume, which would be 13.2 plus V. That'd be the total volume mixing together. This will give me the molarity for the B, which is the base part, the top part. That's what would go up here on top. Okay? For the bottom part, let's get a different color. This one here, this is for the acid. I would say, well, 0.200, oh no. The millimoles, let's just write it this way, of acetic acid, which we just found right there, divided by 13.2 plus V. This will be the molarity for the A section. That's the denominator of my log. What you're going to see is the 13.2 plus V will cancel out from both sides, and I'm going to have one unknown, capital V, that you would solve for. So this goes here, the A part, and the B part goes up here in the numerator. And then you're going to have one unknown. It actually shouldn't be too hard to solve because the denominators here will both cancel. Does that kind of make sense? Okay, cool. Okay, one last question. Or no question. Okay, have a good night.